Stanford University.
All right, so the last time we were beginning to get to the idea of a quantum field. And that's what I want to get to today. What is a quantum field? How is it related to particles? We spent a little bit of time talking about harmonic oscillators. And the basic mathematical tool for quantum fields, for any kind of field, well, quantum fields, for any kind of quantum fields, is the harmonic oscillator, and putting oscillators together to make quantum fields. So we talked about fields on a periodic space. I'm not going to draw the periodic space. The periodic space is one which, after you go a distance L, comes back to itself. It's a useful trick. And the reason it's a useful trick, better than just taking a finite line interval, is because when you have a periodic space, you can have waves which go in one direction, or waves which go in the other direction, without reflecting. And that is the analog of momentum. It's not the analog. It is momentum conservation. So if you want to retain momentum conservation, it's a good idea. If you want to maintain momentum conservation and temporarily put a system in a finite box so that you don't have an infinite volume to worry about, then the right way to do it is periodic boundary conditions. And under those circumstances, a wave, a plane wave, instead of being sines and cosines, will be of the form e to the I kx. K can be positive or negative. A k being positive corresponds to a wave moving to the right around the loop. A k moving, a negative k corresponds to a momentum going in the other direction. Just to remind you, k is not an arbitrary number. It has to come in integer multiples of something or other in order that the wave, when it comes back to itself after going around the distance L, that the wave comes back to its own original value. So if we say that x, in going all the ways around, I said I wouldn't draw it, but I did, the distance around is L, then e to the I kl must be what? No. It's got to be 1. It's got to be 1. At x equals 0, here's x equals 0 right over here. This function is 1. When x equals 0, any exponential of x is 1. And when it goes all the ways around, it better come back to itself. So that means that e to the I kl must equal e to the, let's say, I k0. X equals 0, x equals L. E to the I k0 is just 1. And what does that mean? E to the I kl equals 1. What does that say? That says that k times L must be an integer multiple of 2 pi. E to the 2 pi I is equal to 1. How do I know that? Well, we can just work it out. Remember what the exponential means. It means cosine of 2 pi I plus, 2 pi plus I times sine 2 pi. Cosine of 2 pi is 1. Sine of 2 pi is 0. And so, indeed, this is equal to 1. And in fact, if you put any multiple of 2 pi here, it's also 1. So as long as kl is an integer multiple of 2 pi, this is a periodic function. E to the I kx is a periodic function. So k times L must be equal to 2 pi times an integer, and let's call that integer n. This integer should be distinguished from another n which will occur later. It's the n which counts the number of quanta of each type. All right, this is not counting the number of quanta of particles. It's just counting the allowable wave numbers. This is called a wave number. And all right, so k times L is 2n pi, or k must be 2 pi n over L. That's the condition on k that when you go around, the function comes back to itself. So that's one thing. Incidentally, this is exactly the same thing as the quantization of the wavelength, saying the wavelength has to fit in an integer multiple of times by the time you come back. What's the connection between k and wavelength? Yeah, the wavelength is inverse to k. There's a 2 pi in the relationship. If we turn this over, it's 1 over k equals L divided by 2 pi n. Oh, well, you can work that out. I'll let you work that out. This is the condition on k. It is equivalent to the condition that the wavelength be quantized so that it just fits into the circle an integer number of times. So these are the kind of waves you can have periodically. If we are talking about the waves that are associated with some quanta, then k is related to the momenta. I guess we better work that out. I guess we better work out the relation between k and the wavelength. What is the wavelength associated with a wave like this? Well, it's the distance you have to move before e to the I k goes through one full cycle. So if I want to find out the wavelength of an object like this, the wavelength of this kind of wave, I just say that k times x, or k times the wavelength, has to be k times the wavelength lambda, has to be 2 pi, or k is the same thing as 2 pi divided by the wavelength. So that's the relation between k and wavelength. When wavelength is big, k is small. When wavelength is small, k is big, and there's a 2 pi relating them, but they're closely related. All right, so that's the relation between k and wavelength. Does anybody remember the relationship between the wavelength of a photon or anything else and its momentum? Right. Momentum of a particle, we're making a bunch of connections. The momentum of a particle described by a given quantum mechanical wave, the momentum of a particle is equal also to what? H bar. Well, h divided by lambda, is that right? From last time, yes. We did that. Yeah, h over lambda, but I can express that in terms of h bar, and then there would be a 2 pi h bar over lambda. So you can see that, that p and k are essentially the same thing, except for a factor of k. Okay? Sorry, except for a factor of h bar. All right? In particular, momentum is h bar times k. So if I have a wave described, this is called the wave number. K is called the wave number. All right? If the wave number, and it can be positive or negative, waves moving to the left, moving to the right, corresponding to momenta going to the left or the right. Okay, so that's the basic wave on a circle, if you like, or wave on a periodic space. Now, for each such kind of wave, there can be quanta. Quanta corresponding to particles. How do we describe those quanta? Well, we just describe the number of quanta with momentum p, or equivalently, the number of quanta with a given wave number k. How many quanta are there with a given wave number k? Since k is itself an integer, we have to specify an integer for each integer. Okay? One of those integers is just related to the wave number. The other integer is called the occupation number, the number of quanta occupying that particular wave, if you like, or that particular wavelength. All right, so there are n's which correspond to the quantization of momentum, but there are also n's which correspond to the number of quanta with each momentum. Those are called occupation numbers. So I could write, and I will write, n of k. This is a different n now. N of k. K is itself quantized, but n of k is the number of particles or the number of quanta with wave number k, which in effect means with momentum p, but just remember there is a that p and k happen to be related by h bar. Of course, if I'm smart, I choose units in which k is equal to 1. No, not k is equal to 1. H bar is equal to 1. And then k and p are the same thing. So we often don't even bother to distinguish between wave number and momentum. We speak of k as the momentum of the particle. And
I have a question. So
yeah.
It doesn't matter whether the momentum is that way or this way?
Well, it's k positive and k negative.
Right.
Yeah.
And you that's a factor into your
Say again?
description of the field with these occupation numbers and so on.
Yeah, so you have a collection of occupation numbers for every value of k, including negative and positive numbers. Okay, yeah. Michael.
Yeah, just to clarify, k itself, I think, is not an integer. It's just a multiple of 2 pi over l.
K is not itself an integer.
Wave number is not an integer.
Wave number is not an integer.
It's an integer multiple of 2 pi over l.
That's correct. K is 2 pi over L times an integer. But this integer is not the occupation number. Okay? We could, I don't know what, I don't know any other good notation for integer except n, unfortunately. And so everything which is quantized winds up being called n, except when it's L. But I don't want to call this thing L because it's not L. What is L? L is angular momentum, which is also quantized. So we got to keep track of the two different kinds of integers. One of them, the discrete momentum, and the other, the discrete number of quanta with each momentum. And the way to keep track of it is occupation numbers I will call n of k, meaning the number of quanta with momentum k. K itself is also quantized. Okay? All right, so occupation number, number of particles with a given momentum k. Next, we introduce operators, quantum mechanical operators. For those who know a little bit of quantum mechanics, you will remember that state vectors are linear what shall we call them? State vectors. I will shoot anybody who calls them vectors, state vectors, because we will get them confused with directions in space. Linear elements, let's just call them linear elements. Elements, they are elements of a vector space, but forget that. The state vectors of a system are linear elements that we can add and so forth, but we can also operate on them with operators. We've gone through this at least twice in this series of classes. And the observables of a quantum mechanical system are the Hermitian or real-valued operators which operate on the states. Operate means they are operations which change a state into another state. Now, what is a state? What is a convenient way to label the possible states of a system of quanta moving on such a circle? Is to specify all the n of k. So you can think of it as n1, n of 1, n of 2, where the 1, 2, and so forth refer to the values of k. N of 3. Oh, I also have to put in n of minus 1 and minus 2, don't I? Well, darn it, how am I going to do this? I just have to imagine that this string goes both to the left and to the right. And that represents a state with n1 quanta with the first value of momentum, n2 quanta with the second value of momentum. We don't have to specify what these values of k are. It's just the first one, the second one, the third one, and so forth. The minus 1th, the minus 2th. So that's a quantum state of the quanta moving on the circle. And now there are operators analogous to, not analogous to, but really equivalent to, the harmonic oscillator creation and annihilation operators, the raising and lowering operators. Remember, the harmonic oscillator is described by operators A plus and A minus. I'm not multiplying them, I'm just writing them. A plus and A minus. A plus increases, these are the energy levels of the oscillator. It increases, takes you from 0 quanta to 1 quanta, 1 quanta to 2 quanta, and so forth and so on. And A minus takes you back down. Okay? So, what these operators are, and there's one of them for each momentum, or one A plus and one A minus for each momentum. So they should be labeled as A plus of k and A minus of k. So what does A plus of k do when it acts on a state vector like this? Well, it goes to the kth slot. For example, let's take A plus of 1. It goes to the first slot here and increases the number of quanta by 1 unit. It also does something else. You remember what the other thing it does? It multiplies by something. Square root of n plus 1. Yeah. Yeah. For the minus, it's just square root of n. Right, so I'll remind you to keep track of those coefficients that I explained last time. And as a bookkeeping device, it's a bookkeeping device, the A pluses, the square roots. All right, so A plus of 1, and in general, A plus of k goes to the kth momentum slot. I really should call it A plus maybe of n of k. That's going to get, no, that's bad. That's bad. No. Just A plus of k increases the number of quanta with momentum k by 1 unit, and A minus decreases it, at the same time multiplying by the appropriate square root of n. All right, that's a set of mathematical objects that we have to deal with. And how do we build a quantum field? What is the connection between the quantum field and the A pluses and the A minuses? Well, I'll tell you now a little secret what the A pluses and the A minuses are. In another language, they're the quantum mechanical versions of the Fourier coefficients. The Fourier coefficients of the field. A field on a periodic circle like this can be represented, let's give the field a name. Let's call it psi. Let's call it psi, and psi is a field, it's a function of x, and any such field on a periodic interval like that can be represented as an infinite sum over the allowable values of k. I write sum over k, you say, what values of k am I summing over? I'm summing over the allowable values of k. Of what? Coefficients, let's call them alpha of k, e to the I kx. That's the same as expanding it in sines and cosines. That's psi. And there is another object, psi star. What is psi star? The complex conjugate of psi. Obviously, psi is, in general, a complex thing. E to the I kx is a complex thing. If psi is a complex thing, it has a real and imaginary part. The real part plus I times the imaginary part is psi. The real part minus I times the imaginary part is called the complex conjugate. And that's equal to the sum on k of the complex conjugate of alpha times, what's the complex conjugate of e to the I kx? E to the minus I kx. So to specify a classical wave, let's call this a classical wave, you specify all of these Fourier coefficients. These Fourier coefficients, you don't have to specify separately the alphas and the alpha stars. If you know alpha, you know alpha star. But you do have to specify the real and imaginary part of the alphas. Okay. So a classical configuration of a wave is specified by giving the alphas. The quantum mechanical A pluses and A minuses are the quantum mechanical versions of the alphas. These are observables. Why are they observables? Because if you have a wave, you can measure the amplitude of each of its Fourier components. These are the amplitudes of the Fourier components. Can you measure them? Sure. So they're observables. Or at least the real and imaginary parts of them are observables. Classically, if you can measure the real part and the imaginary part, the whole thing is observable. But strictly speaking, when you do an observation, you get a real number. So an alpha really stands for two observables, a real and imaginary part. The quantum mechanical version of the alphas, I'm not going to write equals. That wouldn't quite make sense. These are classical variables. These are quantum mechanical operators. But instead of writing equals, let's write, I don't know, sort of equals. That means approximately equal. Yeah. Yeah, back and forth arrow. That means in quantizing a system, you replace alpha by A's. So the double arrow means replace by. And same thing here, alpha star. Yeah. Do I have this right? I wonder if I have it right. I wonder if I think I have it right. As we go along, I may decide to change the definition so that this is called alpha star and that's alpha. It's not important because you have the freedom. Let's see. Yep, I'm going to change it. Yeah, the standard definition, and this is a convention, of course. If alpha star is the conjugate of alpha, alpha is the conjugate of alpha star. So there's a matter of definition here that you can choose either way. But I think it's standard, if I remember, to make this identification. Again, it's not terribly important. And then you say the quantum field, the definition of the quantum field is simply replace the alphas by the creation and annihilation operators. A minus of k, A plus of k. Now, of course, of K. Now, of course, we would have to prove that in some sense or another, the classical alphas, in some appropriate limit, the A's must behave like the alphas. In what sense? I can just make this replacement on the blackboard, but you probably say to yourself, why is that the right replacement? In what sense do these quantum mechanical objects behave anything like the classical Fourier coefficients? Okay? Well, in many ways, but let's to see that, we have to go a little more into the dynamics of quantum fields, and we will a little bit. But let's just take it as a matter of definition now, that a quantum field is represented as a Fourier sum where the Fourier coefficients are operators. That makes sense. That the Fourier coefficients are operators, that makes sense, because the Fourier coefficients you expect to be observables. And that the structure of those observables, or the relation between them, is exactly the relation between creation and annihilation operators. The field is an operator, right? Yep. You change the star and make it Hermitian conjugate.
That's a naive question.
Yeah.
So my understanding was that when quantum field theory was introduced, the major breakthrough was that it allowed for particle creation and annihilation. And you've used the terms annihilation and creation.
Right. That doesn't mean that the dynamics will create and annihilate particles. For that, we have to go into the dynamics of these fields.
Okay,
but,
because I've only seen you talk about changing energy states so far.
well, they change the number of particles. What the A's and the A pluses and the A minuses do is they change the number of particles. These things here represent the number of particles with momentum 1, number of particles with momentum 2, number of particles with momentum 3. And what the A's do is they change them. Now, to say that the A's change the number of particles doesn't mean that nature goes around changing the number of particles. These are mathematical symbols which change the number of particles. It doesn't mean that particle number changes. Okay? That's a matter of laws of nature, where the laws of nature permit the number of particles to change. But if the laws of nature do allow the number of particles to change, these operators are going to be very useful in describing those kind of changes. Now, there's other situations, even where the number of particles doesn't change. Well, let's look at this. Let's look at what we can do with these operators. Supposing we want to describe a reaction where a particle scatters. A particle scatters. When it scatters, let's say we have one particle, not a whole bunch of particles, one particle of a given momentum k, and that particle is going to scatter, collide with something, and it's going to come off with another momentum. How do we describe, how might we describe such a process? We might describe a process like that by saying, let's start with a state with one particle. Where shall I put that particle in here? Whatever the momentum of the particle happens to be. If the particle happens to have momentum k7, then I will make it 0, 0. I'll go to the 7th place and put a 1 there, and then 0, 0, 0. That's supposed to be the 7th place. Okay? So this describes a state with one particle of momentum k7, whatever k7 happens to be. Now I want to describe a process where the particle of a given momentum scatters and comes off with some different momentum. Now, so far, we've only been talking about one dimension of motion. We've been talking about motion on a line. Okay, we can do motion on a line, and we can even think of changes of momentum. A particle gets hit by something, and its momentum changes. How can we describe that? Well, we can describe that by saying, we can describe that by an operator which makes exactly those changes. Namely, take an operator which removes this particle. What's that? That's a minus of 7, or k, a minus of k sub 7, but a minus of 7. That removes that particle and then puts back another particle in another momentum state. For example, if it's a scattering where a particle goes from momentum k7 to k9, then we'll put here a plus of 9, or k9. Maybe I should call it, let's call it k. Let's write it that way. A minus of k7, a plus of k9. What does this do? It acts on a state with a momentum with k7 and switches it to k9. So it's a scattering. It's a kind of scattering process, or it does what the scattering process does.
How does that scale in the factor in the
Say it again.
You do the square root is scale and multiply.
Well, here it doesn't matter.
What is that?
Here it just multiplies by 1.
It doesn't multiply the whole thing by some scalar, like
By what?
root of 7.
Say it again.
Well, we showed before that when you do the two operators, you have a scalar multiplier. Square root of 7 or something.
Square root of n7, but n7 is 1. Right. Then, all right, so let's see what this does. It first removes this particle with a coefficient 1. So it gives a plus of k9 times 0, 0, 0, 0, 0, 0. What is this state called with all zeros? It's called a vacuum. All right, so when I speak of the vacuum, it is also the ground state. It is also the state of lowest energy. And in this simple example, we could call it the vacuum, meaning no particles. All right, so the first operator takes a state and makes the vacuum out of it. And then the second operator comes. Now, the creation operator multiplies by square root of n plus 1, right? All right. But we go then to k9. K9 is out here. Its occupation number is 0. So the n plus 1 is just going to give us 1 again. All right, so this operation then gives us 0, 0, 0, 0. But then out at the 9th place, it gives us a 1. So all it's done with coefficient 1 is it's switched the place where the particle is from one momentum to another momentum. Now, if there are situations where these square roots of n come in, and we'll talk about them, we'll talk about what they do. They are important. But in this particular problem, because there was never more than one particle in the problem, the square roots of n don't do anything. Okay, so here's an example then where a scattering process is described by a certain combination of a's. Now let's go a little bit further. Let's suppose that the laws of physics allow for the possibility that the number of particles is not conserved. Okay? Supposing one particle can come in and two particles can go out. Oh, this process, of course, we could have described in another way. We didn't need to go to this complicated story with occupation numbers. We could have just said a particle makes a transition from one momentum to another. But now let's get a little fancier and say the laws of physics permit a new kind of process where the number of particles change. For example, one particle comes in, it might collide with something, and two particles of the same kind go out, but two particles with different momenta. Particle of K1 comes in, and two particles, one of K3 and one of K5, go out. Don't worry too much about momentum conservation. I'm assuming there's something to soak up the recoil, some other object. How would we describe that? That would be difficult to describe in one particle quantum mechanics. One particle quantum mechanics means the quantum mechanics of a single particle. This is possible to describe. There was never more than one particle. One particle went to one particle, but one particle goes to two particles? That you can't describe in single particle quantum mechanics, but you can describe it here. Again, you remove, okay, the seventh particle, and you put in the ninth particle, and you also put in the 11th particle. I don't know why I'm taking only odd numbers. Let's put in an even number. A plus of 16, of K16. So this is a process where a particle of momentum K7 comes in, may collide with something. One might say that that something absorbs the particle. It's just language. This is language. The target, whatever it was, absorbed this particle and emitted two particles, one of K9 and one of K16. So this gives you flexibility, the existence of these operators and this space of states in which the number of particles is variable. It gives you flexibility in studying processes where the particle number can change. A cookie number there. A chocolate chip operator. All right, so if A plus creates a particle of momentum K, A plus of K, what does psi of x do? Psi of x is also an operator. It's a sum of operators, or let's take psi dagger. Psi dagger is made up out of creation operators. It creates a particle of momentum K. No, sorry. A plus creates a particle of momentum K. What does psi do? So to understand that, you have to remember that in quantum mechanics, unlike classical mechanics, you get to add states. States form a linear, I'm going to say it, a linear vector space. That only means that you can add them, subtract them, and multiply them by ordinary numbers. All right? So let's start with the vacuum. I'm not going to write a string of zeros. O stands for O. Okay? And now we act with psi dagger. First of all, what does psi do, incidentally? Psi tries to annihilate a particle, but there's no particle there to annihilate. So it just gives you 0. No state at all. But let's take the creation object psi plus and act on this. All we have to do now is follow our nose, psi plus of x, where x is some particular value of position, some specific value of position. Let's see what it does. Yeah, psi dagger. Well, we just substitute for psi. We write sum over k of a plus of k O times e to the I kx minus I kx. But what is this object here? This is an object which just represents one particle with momentum k.
How can you take the e2ikx out of this?
I didn't need to take it outside. Good point. Sum e to the minus I kx. Okay. This is a one-particle state with momentum k. What happens if I superpose one-particle states with momentum k with a set of coefficients e to the minus I kx? Does anybody remember from quantum mechanics what happens if you superpose or add up state vectors corresponding to a particle of momentum k, and you add them up with coefficients e to the minus I kx? Anybody remember? No, k's are momentum states. You got the right idea, but you wanted to... These are momentum states. This is a momentum state. But what happens if you add momentum
It
states?
takes psi to the momentum space. Doesn't it take psi, the operator, to the momentum space operator?
This is a momentum state. If we were doing one-particle quantum mechanics, we might just call this a particle of momentum k. One particle. Right? In this problem here, I never have more than one particle. I act with this operator. It gives me a superposition of one-particle states. Each state that appears here is a one-particle state, and it's a one-particle state with momentum k, and I'm told to add them up with e to the minus I kx. It's a position state. It's a state with a definite position. What's the position? X. Right. If you add up momentum states with an e to the I kx, that gives you a position state located at position x. That's one-particle quantum mechanics. Okay. So that tells us then what psi dagger of x does. Psi dagger of x creates a particle at position x. It creates a sum of particles. It creates a coherent quantum mechanical superposition of states with momenta, all the different momenta, all the allowed momenta, right, all with coefficient e to the minus I kx. Incidentally, what's the probability for different values of k? All the different values of k have the same probability because the coefficient here, when squared, all give 1. Right? So this is a linear superposition of states with different momenta where the probability, remember what the probability is, the probability would just be the square of this, or it times its complex conjugate. This would be just a state with a uniform probability in momentum space. All right? But it is a state with a particle at a definite position. Okay, so this is getting pretty now. The a pluses of k and a minuses of k, which are the Fourier, which are to be interpreted as the Fourier decomposition of psi of x, those are creation and annihilation operators for particles with definite momentum. Okay. Psi of x and psi dagger of x are creation and annihilation operators for particles of definite position. So if you wanted to create a particle at position x, you would not do it with a of k, but you would do it instead with psi dagger of x, which you can rewrite in terms of a's of k, but it's just giving you the quantum mechanical superposition of momentum states that adds up to a position state. Okay? That's the basic idea of a quantum field. In relativity, it's a little more complicated, but if we don't worry about the complications of a special theory of relativity, don't worry about them yet, then the quantum field psi dagger of x is a creation operator for a particle at position x. Yeah.
At X, and we're talking about a periodic or box.
Yeah, in this case, yeah.
So would it be a particular number of waves, or it would be it's not a spot on that circle?
It is a spot on that circle. Yeah, it's a spot on that circle. Now, eventually, right. Eventually, we can make the circle bigger and bigger and bigger. What does that do? Remember, the allowable values of k were 2 pi integer over L. Okay, so they're spaced by a spacing 2 pi over L. That's the spacing. As L gets bigger and bigger, the spacing gets smaller and smaller, and eventually you can have essentially any value of k, or at least for any value of k, there's a state arbitrarily close by. So making the ring bigger and bigger and bigger is equivalent to replacing the discrete values of the momenta by continuous values. And what does that entail for an equation like this? Right. It means that you integrate over k instead of summing over k. But it's good the first time around to think about it discretely. Once you know and you understand that, you can replace it by integral dk, but let's not do that yet. Okay, next step. Next question. What if psi creates a particle at position x? Obviously, psi dagger, no, I take that back. If psi dagger creates a particle at position x, what does psi do? It annihilates a particle at x. Right. Okay, let's think now about the possible kinds of reactions. Reactions, I now mean particle reactions that we could think about, but in the language of psi of x. Here's a possible reaction. You tell me if you think this is a likely thing. A particle comes in, and when it hits a target, where the target happens to be localized, very precisely localized, at position x, that particle disappears, and then off on Alpha Centauri somewhere, the particle goes off here, and somewhere on Betelgeuse, another one goes off over here. That sound likely? No, it doesn't sound likely. No. It's what we would call non-local. It violates the rules that signals can propagate in arbitrary kind of crazy velocities. What's the right thing to think about? The right thing to think about, if you want to preserve in your theory a very precise notion of locality, is that a particle is absorbed right over here, and then 2 particles are emitted. The emitted particles will be absorbed, will be emitted from the same spot. Now, you might want to loosen that up a little bit for one reason or another and say, well, maybe it only means that they're emitted within a certain region of that. But in fact, the precise notion of locality in quantum field theory is that when a reaction happens, it happens very much at a spot like this. So how would we describe this reaction? One particle comes in, is absorbed at x, 2 particles go out, are emitted from the same point. We could use these operators to describe more non-local processes, but if we want this local process, what do we write? We write that the first thing that happens is a particle is removed from the system, that's psi, at point x, and then 2 particles are put back in at position x. That would be psi dagger of x, psi dagger of x. That might act on a state with some, sorry, not the vacuum state, but a state with with a particle in it, okay, with some particle in it. Let's try to figure out, here's the exercise. A particle with momentum k comes in. I want to know if that particle with momentum k is absorbed at position x, what is the final state? What is the final state, and what is the various probabilities for this final state to have this or that momentum? Right? So, what we have to do is very simple, in fact. We have to first of all say there's a particle with momentum k here. That means 0, 0, 0, and in the kth slot there's one particle. That's the first step. Write down the initial state. Step number 1. Step number 2, substitute for these these are called local field operators because they're localized at a position, substitute their expression. If we're trying to find out information about momentum, substitute in their expression in terms of momentum creation and annihilation operators. So let's do that. Okay, so psi of x, first of all, is sum over k. And again, sum over k means sum over the allowable values of k. A minus of k e to the I k x. That's psi of x. What x do I put in here? The x at which the reaction is happening. All right, so what kind of a reaction could we imagine? Can you give me an example that would make some sense? Well, let's not talk abstractly. Let's talk concretely. Yeah, we could have, okay, so then we would have to have operators describing different kinds of particles. Right, no, but I mean, you've got the right idea. But let's use photons. Now, this is not quite the right description of photons, but let's ignore the photons are relativistic particles. This is more appropriate for non-relativistic particles. Let's ignore that. All right, so a photon comes in, hits an atom, localized at a point, and from that point, 2 photons go off. Okay? All right. So the first photon is the photon which we put into the system to begin with. Okay. What comes next? All right, so we take this field operator. That's the field operator which absorbs a particle at position x, and we allow it to strike this initial state, 0, blah, 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 1, 0, 0, 0, in the kth place over here. Now, this is a sum of k. This k is different than this k. In what sense is this k different than this k? Here we're summing. This is a dummy index, just a summation index. This is some definite k, let's call it k initial, the initial momentum of the particle. Okay? But that's the first step. Then, once we work that out, we'll have to hit it with psi dagger of x times psi dagger of x, and here's psi dagger of x. So let's write that down. Since k is a summation index, we should use a different letter. We shouldn't use k over again. Let's call it L. These are summation variables. Doesn't matter what you call them. All right? I just don't want to repeat the use of a summation variable over here and call it the same thing again. So we have summation for the first operator, summation over L, a plus of L, e to the I L x. That's this one, e to the minus I L x. And what about the second application of psi dagger? We just have to write the same thing again, but again we better use a different summation index because we're not allowed to repeat the use of a summation index twice. That wouldn't make sense. It would mean, so we have to repeat the same thing. What shall we call the new summation index? KL M? All right, M doesn't mean mass here. All right, it's wave number. M A plus of L e to the minus I. Oh, M, sorry, M e to the I minus I M X. All right, what kind of state does this create? Let's see what kind of state it creates. First of all, here's a big sum. Which terms of this sum give something which is not equal to 0? What? K sub I. Only if this k here is not the same as this k, for example, if this is k sub 13, if that corresponds to the 13th slot, then what happens when I apply k1 e to the minus I k1? Well, it tries to absorb the first particle, but there is no first particle. Same for the second one. Same, only the 13th slot is occupied, so only k sub 13 will survive, or a sub 13 will survive when it hits this state. The rule is an annihilation operator has to find something to annihilate. So this really reduces to one term. It's summation, it's not summation, one term, and it's the term with a minus of k13, or k initial, just k initial. K initial times e to the I k initial x acting on this state. Now what does this do? What does the annihilation operator do when it hits this state? It just removes that particle with a coefficient of 1. So we just erase it and erase the particle, and all that's left is a state with no particles times e to the I k initial x. But now we have to apply this. Okay? We have to create particles, summation L, well, just exactly the summation that we have here. This part of it we're finished with, and it just gave us an e to the I k initial x times the vacuum. Okay, now what do these do? What does this one do first? It puts in a particle of momentum L. Okay, so it puts in a particle of momentum L. That's what that's what A plus of L does. And what does this one do? It puts in a particle of momentum M. So the whole thing in the end is we keep that, e to the I k initial x e to the minus I mx e to the minus I lx, right, times 0, 0, but now when 1, 0, 0, 1, 0, whatever, summed over L and M. Which two sites are occupied? L and M. L and M. So what it's given me is a sum over L and M. And now let's just replace this. Let's just call this a two-particle state with a particle of momentum L and a particle of momentum M. The notation is now, I've used a different notation. I'm labeling this now as two particles, one with momentum L and one with momentum M. And it's a sum over such states. The sum has not gone away, but it's a sum over L and M with a coefficient, with a functional dependence, e to the I k1x minus mx minus lx altogether, sum on m and l, e to the I k initial minus m minus l x times lm. Yeah.
Do the two creation operators commute?
Yeah, the two creation operators commute. Creation operators commute. Okay, that's a very good question. The rule is all creation operators commute with each other. All annihilation operators commute with each other. And creation and annihilation operators commute if they refer to different momenta. Okay? If they refer to the same momenta, then they don't commute. Yeah.
There's a special case when m happens to be equal to L.
Say it again. Ah, for the good point. Good. Okay. Right. This is correct if m does not equal L. What is this? What is the probability for different values of L and M coming from here?
You have to have conservation momentum, so they seem like
No conservation momentum here because the atom which absorbed the photon could recoil. Right, so the heavy atom could absorb any amount of momentum. All right, so there's no conservation of momentum. What this is up here is the change in momentum, initial momentum minus final momentum. It is, of course, the momentum carried away by the atom. All right, but this function here, which is a function of m and L, is just a phase. Its magnitude is 1. So that means there are equal probabilities for all values of L and M. When you square it, you can think of this as the wave function for a two-particle state. The wave function is a pure phase, and all values of the momenta have equal probability. Okay? Except, not quite. What about if L equals M? Then I made a mistake. And the reason that I made a mistake is when, all right, so let's go to that particular case. Let's take one particular case where L and M are the same. Of course, there are many such cases. M could be anything. But I want to focus on those contributions where the L and the M are the same. All right? Then there's going to be the factor e to the 2imx, e to the minus 2imx. That's just because L and M are the same, so there'll be the same factor of the same kind of factor there. But one thing will be new. What is it? What happens when A plus acts the first time? It gives me a particle in the mth site. What happens if A plus acts again?
It's going to act on a different.
No, it has the same momentum. It creates another particle, but it gives me a square root of 2. Right? It gives me a square root of 2. After the first one acted, now I take the second one. It looks for a particle of momentum m, and it finds one. Damn it, it finds one. So there's one particle present already. Remember, the rule is that if it finds n particles here, you give it a square root of n. Square root of n plus 1. Square root of n plus 1. So what's the square root of n plus 1? Square root of 2.
Wouldn't they have to be L and M be off by 1? difference.
No,
Because
no,
you
no.
created n plus 1.
What's that?
And the a plus of n gives you square root n plus 1 operating on n plus.
Don't confuse particle number with momentum number. Right?
Okay,
Right. Okay. Right. Right. So, right. So, for the special case where L and M, where the two particles come out with the same momentum, it could be that momentum, it could be that momentum, it could be that momentum. If they come out with the same momentum, there's a factor of square root of 2. What does that mean about probabilities? Yeah. You square the coefficients of the state vectors to find probability. That's odd. If two particles go off in arbitrary directions, not the same, with different momenta, or different momenta, different magnitudes of momenta, there's one value of the probability. But if you produce two particles with the same momentum, then the probability is twice as large. These particles like to be in the same state.
So this is always indistinguishable. They have to be indistinguishable. Two different kinds.
This is the description of indistinguishable particles. Right. This is very much the description of particles which are not distinguishable from each other. Okay. So the production of two photons in a collision is twice as probable if the two photons come off in the same state as if they came off in different states.
You talked about the commutativity of the operators.
Yes.
In a complex reaction, how do you know which order to apply them?
Well,
But if you've got particles being annihilated, particles being generated, is it obvious always the causality involved?
no, it's not obvious what order. But with different orders, you can always commute them until they come out in the order in which all the annihilation operators are to the right and all the creation operators are to the left. That's called normal ordering. And in that ordering, the first thing you do is you let the operators eat particles and then spit out some new ones. So normal ordering, but we'll come to that. We'll come to that.
If the probability of any L and M are all the same, then they're sort of like 0 or very infinitesimal. So what does twice that mean?
Okay, that is a good question, but for that I ask you to keep in mind the example in which the momenta are quantized. For example, these could be photons in a cavity where the momenta really are quantized. Okay, so if a particle in a cavity where the momenta are quantized, if a particle or a photon comes in, hits an atom, and creates two photons, it will be twice as probable for the two photons to be in the same discrete energy level as to be in different levels. So, no.
It seems to me that there's only one case where L equals M equals 3.
Say it again?
Only one case that comes up in the sum where L equals M equals 3. But there are two cases where one of L and M is 2 and the other is 3. In other words, if L and M are different, then they show up twice in the sum.
Okay, so what, let's see. Yeah, you're right. So let's see what that says. Let's see. If L and M are different, okay, good. So let's do that case. That's going to give you a, what kind of factor then? Right, you are right. So let's see. So what? So if we have A of 2, a dagger of 2, a dagger of 3, we have to add to that plus a dagger of 3, a dagger of 2. That's true. So it looks like this one is more probable. But it's not as much more probable as it would be if that square root of 2 wasn't there. So let me give you another example where you really see this is, yeah, I actually think you're right that the ones with different momenta, because there are 2 different ways to do it, may be more probable. But let me give you another example where you can see these square roots of n in action. Supposing we have a particle which can decay. So we have some sort of particle which can decay and emit a photon. How do we describe that? We typically describe that by just a psi of x. Suppose it can emit 1 photon. Well, let's see, one photon. 1 photon is enough. 1 photon is enough. All we want to do is create a photon at point x. Let's create a photon at point x. All right, so that's just psi dagger of x acting on the vacuum. This would be the decay of an object producing a photon, or just the emission of a photon from a point x. What does this give? This gives sum over momenta, k, creation operator of momentum k, e to the minus I kx, acting on the vacuum. The vacuum means the state with no photons in it, for example. All right, what does this give? This gives the sum over k, e to the minus I kx, times a state with a particle of momentum k. Obviously, equal probability for all possible momenta k in this particular case. Okay? Equal probability for all momenta k. Now let me do something else. Let me suppose that there was pre-existing a particle of momentum L. There was pre-existing in the cavity, there was a particle of momentum L, and our atom decays. There's an atom that's going to decay and emit a photon. Right? But there's already a pre-existing photon of momentum L. The first calculation told us that in the simple model situation, we have equal probabilities for the emission of all possible momenta. Don't worry about conservation laws here. We've abandoned them a while back. Tells us that there's nothing distinctive about any of the momenta. They all have equal probabilities of being emitted. But now let's suppose there's already a pre-existing particle of momentum L. Okay? Then that means we have to operate on this here with a particle that already has momentum L in it. There's a 1 here someplace. Okay, supposing k is not, this is the Lth place over here. Supposing k is not equal to L, then this just creates a particle of momentum k with no square roots of anything, because it created a particle of k where there was no particle of k. So the square root of n is just square root of 1. Right? And what does it do? It creates a state with an e to the minus I kx times k and L. The L particle is still there, and the new particle is k. But now supposing we look for the term in this sum where k is equal to L, then what do we get? Then we get a square root of 2. Then we get a square root of 2. So this is correct as long as k is not equal to L. We get a state with 2 particles with a wave function e to the minus I kx. The original Lth particle is still there. It was just a bystander. And a particle of momentum k was emitted. It was emitted with an amplitude e to the minus I kx, a quantum mechanical amplitude e to the minus I kx. But what about the possibility that k here is equal to L? Then what happens? By a factor of 2. By a factor of 2. Because now this A of k is A of L. That term is just A of L. There's already a particle there of momentum L. And so you get square root of 2. That's what these operators do. That's what these things do. They give you factors of square root of the number of particles of the type each time one of these things acts. So if there was particles all over the place here, then you would have an enhanced probability for producing particles of the kind which are already there. Yes. That's called, yes, this is called stimulated emission. Stimulated emission.
But the particle L has to be at the same location, right?
Has to be of the same momentum in this case.
And in the same location.
Can't be both in the same position and the same momentum.
So it can be like, 1 mile away and it will still affect.
Well, really particles come out in wave packets. They don't really come out in discrete momentum eigenstates. But in a cavity they come out with definite momenta. And this is a real effect. This is a real effect that if there are particles present of filling the cavity, then the decay will preferentially happen into photons which have the momenta of the particles in the cavity. The more particles you have in the cavity of a given momentum, the more probable it is that the next particle will come out with that momentum. So if instead of having 1 particle in this Lth slot, we had 100 particles in this Lth slot, then we would get a factor of square root of 101, I guess. Yeah, square root of 101. And the probability would be 101 times larger that the atom decays into the state, photon, with the same momentum as that 101 particles. Okay, so you can figure out more generally what the answer will be. That's called stimulated emission. And what it means is that just the presence of particles of a given type will increase the probability that a decay takes place, but only when the decay takes place with the final momentum being the same as one of the momenta already there.
What I gather here is that 2 new particles will still prefer to have different momenta than each other.
Yeah, but not as much as if that extra square root of 2 wasn't there.
Right, but then they will be sort of attracted to existing momenta.
Yeah, it's not a real legitimate attraction of any kind. It's a statistical effect. It's the effect of identity of particles. Now particles, not all particles have this same tendency, incidentally. Particles come in 2 kinds. There are fermions and bosons. Bosons are particles described as I described them here. Creation and annihilation operators with the mathematics of the creation and annihilation operators being the mathematics of harmonic oscillators, particular square roots of n, with the creation and annihilation operators having the algebraic commutation relations of harmonic oscillators. Then you have this tendency, this is very, very general tendency, that the more particles you have, the more likely it is you will decay or produce particles of the same momentum. Same thing happens in scattering reactions. If you have a scattering reaction and it tends to make particles of different momenta, if you already have momenta present of a certain kind, it will tend to preferentially cause the the products of collision to come out with the momenta of the particles there. Incidentally, I said it's called stimulated emission when a particle, when an atom decays in the presence of already pre-existing photons. That enhances the probability for it to decay. When there are no photons present, then it just decays with the probability, with the coefficient 1. That's spontaneous emission. So spontaneous emission is the emission which is unaffected by additional particles because there are no additional particles. Spontaneous stimulated emission is the tendency for other particles to stimulate the emission and make it happen with a higher probability. There is a classical analog of this, incidentally. If you have an atom which is radiating even just classically, and you have an electromagnetic wave passing by it, the electromagnetic wave will vibrate will shake the electrons and cause them to radiate with a higher probability than they would have radiated, or radiate faster than they would have radiated without that electromagnetic wave going past. And in fact, it will tend to make the emitted electromagnetic wave come out with the same direction, same moment, same wave number. So it really is a quantum mechanical version of something that was known classically, namely just that a pre-existing wave will excite the system to radiate more, just because the pre-existing wave will vibrate the electrons. Okay, particles of this type, which have the tendency to come out in the same state, particles that they don't really attract. It's not that they attract. That would be a wrong language. But which have the statistical probability because of these square roots of n to like to be in the same state, those are called bosons. They're characterized by creation and annihilation operators. Let's write down the mathematical rules. There's the mathematical rules of bosons. For each momentum, there are creation and annihilation operators. The creation and annihilation operators have the property that all creation operators for any momenta commute so A plus of k times A plus of L is the same thing as A plus of L times A plus of k. That's true if k equals L or k doesn't equal L. Same thing with the annihilation operators. But an annihilation operator with a creation operator, they do not commute. Now, do you remember what we found for the harmonic oscillator when we did it? Just one oscillator, A minus with A plus. We got one. One. All right. This is 1 if k equals L and 0 otherwise. So the rule is they always commute if we're talking about different momenta. If we're talking about the same momenta, then an annihilation operator and a creation operator do not commute, but have a 1 on the right-hand side. We can write that in the form delta KL, where delta KL is the Kronecker delta, the symbol which is 1 if k equals L and 0 otherwise. This, together, delta KL, together with the definition that psi of x is equal to sum of, I guess, A minus of k. Is it e to the plus or e to the minus? What did I have written? I think e to the minus ikx, if I remember correctly. Okay. With that definition, this basically defines the simplest quantum field theory. Psi is a quantum field, and its job is to create and annihilate particles. Okay. One more thing about bosons before we go on to fermions. Fermions are a kind of particle which are different, obviously, otherwise they wouldn't have another name. One more thing about bosons. Let's look at psi dagger of x. Psi of x integrated over all space. What is that object? Okay. Now, I know what that object is. I wouldn't have written it down if I didn't know what it was, but let's work it out. Let's pretend we didn't know what it was and see if we can work out what it is. Psi are quantum mechanical operators. This is an observable. Okay. Let's work it out. It's equal, from the definition of psi, into, let's see, sum. Oh, I think I want, no, that's right. Sum of a plus of k, I think it's e to the ikx. I keep getting confused about the pluses and minuses. I'll probably make mistakes. That's psi of x. That's psi dagger of x. What about psi of x? Oh, it's a minus. Good. All right. Oh, a minus. It wouldn't make any difference for this calculation.
The sign on the A is opposite of the sign on the E.
Yeah. It's true. It's true. That's right. The balance of plus and minuses.
It's not just balance, it's conservation going from side to side dagger.
Yeah, it is. Okay, so this is sum over k. Then there's another one which is sum over L, which is the annihilation operator, a minus of L, e to the plus ILX. And this gets integrated over x. Now, let's see if we can examine what that quantity is. This is integral dx. The only x dependence here is in these coefficient functions. All right? So what we really need to know is what the integral e to the ILX, e to the I L minus k x dx is. That's the integral that appears here. E to the ILX, e to the minus IKX. That's this, integrated dx. That's the integration that appears here. What do we integrate? We integrate over all of space, which means over this circle of length L. So what do we get if we integrate this over a circle of length L?
You get full sine waves or multiple. You get multiples of the full.
Well, supposing, first of all, k is equal to L.
Get out.
So it's 0.
You get L.
2 pi L?
Not 2 pi, just L. Just L. So you get L if k is equal to L. What if k is not equal to L? You get 0. Why? Because this will be sines and cosines, and if you integrate a sine and a cosine around an integer multiple of wavelengths, you get 0. Both sines and cosines are positive as much as they are negative. So what is this thing? This is delta KL times the length of the interval. All right, so that means when we do this integral, it's going to pick out only the terms where k and L are equal. That's what this means. It's going to give us a factor of big L. So it gives us L times the sum over k. But now it's a single sum and not a double sum because k has to be equal to L. And what's it going to be? It's going to be a plus of k, a minus of k. Do you remember for the harmonic oscillator what a plus times a minus was? the occupation number. A plus times A minus is the occupation number, is the number of quanta with momentum k. If you go back to your notes, A plus times A minus, if you work out all the square roots of n's and things, A plus times A minus acting on any state just gives you the same thing as the occupation number. So A plus times A minus is the occupation number, the number of particles with momentum k. What if you sum that over k? Total number of particles. Yeah, it just counts the number of particles, total number of particles. So this object here, if I divide it by L, I have to divide it by L because of this L which appears here, that is equal to the number of particles. Total number of particles. Now, there are conventions where you absorb this L into psi, and there's a more normal I have been following a particular set of conventions. It's led me to have this 1 over L out here. That's all right, we can leave it there. But basically, psi star times psi is a counting quantity. It counts the number of particles. It's an observable. It's a quantum mechanical operator. But all it is the number of particles. Number of particles may or may not be conserved. So in general, this integral can change with time if particles are absorbed and annihilated, or absorbed or created. On the other hand, if the number of particles is conserved, then this is a conserved quantity. So this is the thing which counts the number of particles. Apart from this L, would you give a name to psi star times psi itself?
Probability density. Probability density.
You could call it the number of particles at point x, but that's not such a good idea because, you know, the density of particles at x. Right. So that's, apart from a factor of L, which I will ignore, just it'll go away when we replace sums over k's by integrals over k. But apart from a factor of k, psi star psi, let's just say psi star psi is proportional to, equals the density of particles at x, psi star of x, psi of x. And it's a quantum mechanical operator. And that's it. That is the simplest of all quantum field theories. Right? A bosonic quantum field theory where the fields are made up out of creation and annihilation operators. There's a psi, there's a psi star, and you can work out, incidentally, it's fun to work out the commutation relations between psi of x and psi star of x. We know the commutation relations of the A's. The psi's are built out of the A's. It's interesting to work out the commutation relations of the psi's. Okay, so that, we'll go on a little bit. I got here.
That's the density of particles of x.
That's the density of particles of x. Now, as I said, this whole machinery so far assumes there is one species of identical particles. Identicals means they're all the same kind. They're identical except for the fact that they might have different momenta or different position, but you wouldn't want to build into a single quantum field both electrons and photons. This might be the field for photons. Now, because of relativity, we have to modify it a little bit. This would not be the field of electrons because electrons are not bosons, and they have to be dealt with differently. Okay, that's the basic theory of bosons. They are described by harmonic oscillator creation and annihilation operators, which are the Fourier coefficients of the field. They like to, in some statistical sense, they like to come out in the same state. If there are already particles present, that will enhance the rate of production of particles with the same momentum. And the creation and annihilation operators have definite algebraic properties, commutation relations, which I've listed here. That's it. That's the whole theory of a very simple quantum field. Again, I emphasize that you can use it to describe reactions in which particles are created and annihilated. Yeah.
So this is all 1D, initially one-dimensional?
Yeah, everything's one-dimensional now, but that can be immediately changed just by putting in more x's. Right. There's nothing special about that. All right. I see people, there are some people who have to go, and I don't want to start a new subject while there are people going, but perhaps we can spend a little while talking about something, whatever you want to talk about, which is not in linear progression.
Is fluorescence related to the simulated emission effect, or it's different?
I don't think fluorescence is. No, transparency is simply interference. You can have a thing which is transparent to electrons. You can have a thing which is transparent to... Okay, so what other things in nature are bosons?
Photons, pions, alphas.
Lots of things. Higgs boson is a boson. The X boson, the Y boson, lots of things are bosons. Gravitons are bosons. We say that psi or psi dagger and so forth is an observable. That means that the field psi is kind of like the electromagnetic field. You can observe it. You can do an experiment and measure psi. Okay? When does psi behave like a classical thing? Now, there's a problem about measuring psi. Its components don't commute with each other. Its real and imaginary parts don't commute with each other. And you can't simultaneously measure two non-commuting things. All right, so psi and psi dagger don't commute. That means the real and imaginary parts of psi don't commute. How can you measure psi if the real and imaginary parts don't commute? And the answer is you can't. You cannot. You also can't measure x and p at the same time. What is the, or for that matter, the harmonic oscillator variables a and a dagger, or a, even a, you can't measure because it has two non-commuting, a real and imaginary part. What is the situation? Let's take the harmonic oscillator first, in which the harmonic oscillator variables behave classically, and in an approximate sense you can measure both a and a dagger, or for an ordinary, yeah, well, what is the situation? When the oscillator is highly excited. When the oscillator is highly excited, and that's the situation in which the number of excitations, a times a dagger, is much, much larger than h bar, is much, much larger than the right-hand side of the commutation relations. Okay. You can't precisely measure these things simultaneously, but just in the same sense that you can measure x and p approximately, as long as you don't violate the uncertainty principle, you can measure the components of fields approximately, as long as you don't violate certain uncertainty principles. Well, what does that in practice mean? It in practice means that you can measure these things as long as the degree of excitation, as long as the field strengths are large by comparison with the uncertainties, large by comparison with the obstruction in measuring them both simultaneously. Right? What does it mean in terms of photons? It means lots of photons, right? That's right. When you have a sufficiently large number of photons, then approximately you can measure the different components of the field simultaneously within certain errors, but those errors may be a lot smaller than the magnitudes of the fields themselves. So the observable quantum fields, thought of as things that you can measure, psi and so forth, those behave like classical fields when the number of quanta is very large. It makes sense. When the number of quanta is very large, the field psi behaves as if it were a classical wave field. It's only when the number of quanta is small that you see their discreteness, and that's when psi does not behave like a classical field anymore. Okay, so that's the setup. Psi is a quantum mechanical operator which does behave classically under certain conditions. It is a measurable quantity, or at least parts, some components of it are measurable, and it can be approximately measured, all of its components simultaneously, as long as the number of photons is much larger than the uncertainties dictated by the uncertainty principle. This is an uncertainty principle. It tells you that the components of A and A dagger, the real and imaginary parts, can't be simultaneously measured. Here's the point. A times A dagger A, is the number of particles. That means, roughly speaking, the magnitude of A is like the square root of the number of particles. As long as A is much bigger than the right-hand side here, or as long as A times A dagger is much bigger than the right-hand side can largely be ignored for many purposes. And that's the situation where A behaves approximately classically. Okay. Any other questions? Yeah.
Is that N the N?
That's the N. That's
the initial state or the final state that you started with?
Well, as long as the number of quanta doesn't change too much, it doesn't matter.
Yeah. If you go in the other direction,
which is,
supposing you start out with a state of 0, 0, 0, 0, the ground state.
That's a highly quantum mechanical state.
Well, okay. Supposing you apply a destruction operator to that state.
Yeah.
I thought I heard you say that
you
get no state.
You get 0.
Wait, you get the lowest state with no particles in it, or do you get no state at all?
You have to distinguish now. Good. The state 0 is a state with no particles in it. It is not the same as the state 0. All right? This state is the ground state of a harmonic oscillator. Its norm is 1. It's not the 0 state. The 0 state is O minus O. This is just a vector which I've labeled as O. It is not the 0 vector in a vector space. It's the vector describing no particles. That's different than the 0 vector. Very different, very, very different. The 0 vector is no vector at all. It doesn't describe anything. This is a perfectly good normalized vector describing no particles, or the ground state of the system.
It seems like there are two states floating around. Or two kinds of states. One is the field.
That's not a state. That's an operator. The field is not a state. It's an operator. Yeah. In quantum field theory, fields are operators.
Okay, so that's not a state. And we have this other thing which is a state.
Yeah.
That they operate on.
That's right. That's
and
correct.
That is
right.
Reality. I mean, it's
I'm not. What, reality? What is that?
Reality is getting to Stanford from Berkeley.
When you take a regular model, periodic, and try to apply it to the real world, like you can say that the capital L is something like the size of the universe.
Oh, yeah.
But it's not very useful.
No, that's not useful at all.
So how do you use it in practice, like with the size of cavity, or when would you use?
Well, a more common situation is when you have a cavity with reflecting walls. Okay, so that's a common situation. But you could imagine electrons moving around on a wire, on a closed wire. That would be an example.
But doesn't the limit on L influence the number of possible states?
Say it again.
Putting a limit on big L
Yeah.
defines the number of possible states.
Putting a limit on big L. No, it doesn't. No, it doesn't. It doesn't put a limit on the number of states. What it says is that k, the allowable values of k, have to be 2 pi over L times n, and n can be any integer. What it does is it limits the number of states with momentum below a certain momentum. So if you were to say the largest momentum I'll ever want to think about is some large amount of momentum, I never want to allow more momentum than that, then this would limit the number of states. But as long as you can have arbitrarily high momentum so that n can be arbitrarily large, it doesn't limit the number of states. Yeah.
For a particular value of k,
Yeah.
when we did the harmonic oscillator, we started with x and p, and then we derived the a plus and a minus.
That's right.
Go the other way. Here we start with the a plus and a minus for a particular value of k. What corresponds to the x and p in our case?
Okay, good. The x and p's, right, that's the real and imaginary parts of the field. In other words, the field psi, one piece of it has a pluses, and the other piece has a minuses. I use this equal, just, you know what I mean. All right. If you add, oh, sorry, psi dagger, plus. If you add psi to psi dagger, of course, you get the real part of psi, and that's a plus plus a minus. That's like x, or maybe it's like p. That's ambiguous. The real and imaginary parts are the two conjugate variables. And they're the two variables, the real and imaginary part are the two variables which have a distinct uncertainty relation between them. So psi dagger plus psi dagger plus or minus psi are two distinct objects. They're the real and the imaginary part of psi, and they correspond to the x and p of the oscillator. That's a good question, yeah.
I just want to go back to this question. For field theory, we're actually going to have an infinite number of these loops representing 3 space in reality, right?
If it's 3-dimensional space,
or
sure.
4 space, yeah.
Right.
We don't try to represent the universe.
Yeah, no, but what you do for 3-dimensional space, let's start with 2-dimensional space, okay? For 2-dimensional space, what you would imagine the analog of the circle is the torus. The torus, you usually think of the torus as a donut, or the surface of a donut. But from a mathematician's point of view, what a torus is you take a rectangle in space, and you identify the left edge with the right edge, and the bottom edge with the top edge. You can think of it as first cutting the torus. Imagine cutting the torus like that. Of course, we're talking about the surface of the torus. Who asked me? Yeah. All right, so we take the surface of the torus and we lay it out. What happens if we cut the torus through and sort of open it up? Well, we get a piece of a cylinder, right? And now we cut it, but we remember that this edge is to be identified with that edge. Then we slice it through here and open it up. But remember that the top edge has to be identified with the bottom edge. So a torus is a rectangle in which we remember that this point is the same as this point is the same as this point. And for example, if we were talking about a classical particle which left the torus over here would reappear over here. It would come here, it will reappear down here. That's the same as a classical particle just moving around on a torus. It's got two directions of periodicity, and for this object, both components of the momentum, the x and the y components of momentum, would be quantized. So that's the way to think about a torus, as a rectangle with periodic identifications, or with identifications across the... and of course, if we had a field, we would require the field at this position to be the same as the field at this position, the field at that point to be the same as the field at that point, and so forth.
That's kind of like what I was asking. Do you represent space, or do you represent the objects in space?
Do you represent space or the object of space? Yeah, we're talking about space, but the only reason for making it periodic is to avoid questions of infinity, and eventually we'll make the space infinite by replacing sums by integrals. Incidentally, there's the notion of a three-dimensional torus. A three-dimensional torus is just a cube with identifications. This point is identified, well, you just identified, this face is identified with that face, the top is identified with the bottom, and the front is identified with the back. So tori can exist in any dimensions. And the notion of a periodic particle moving in periodic space is just the notion of a particle moving within the interior of a cube, but in such a way that when it reaches the edge of the torus, or the edge of the cube, it reappears at the opposite end.
When we go to divide space into its periodic representations of these oscillators, the fields, is there one that one uses? Here we haven't specified anything mapped to any physical reality. Is one chosen by everybody when they go do...
One what chosen?
Is a quantum, a true physical quantum chosen when doing field theory work?
No, remember quanta are the particles. The quantas are the particles. They can change. They come and they go. They're created, they're annihilated, they're radiated, they're absorbed.
Let me try expressing it this way. Is there a grid size for space that everybody uses?
Well, that of course is a very, very speculative question. My own answer would probably be no, but I think you're asking probably questions about length scales of Planckian size and so forth, and that's way beyond what we're talking about here. So most likely quantum field theory just breaks down by the time you get to such scales. It just probably doesn't make sense. So that's, we're talking about situations of, let's say, modest length scales. Scales of 10 to the minus 13 centimeters, 10 to the minus 20th centimeters, 10 to the minus 28th centimeters, but not 10 to the minus 33 centimeters, where that is the Planck length.
But the math itself, abstractly, doesn't break down. It's just that it hasn't been lined up with any kind of physical result.
Right. But for almost all practical purposes, to take space to be continuous rather than discrete. Incidentally, it's momentum which was discrete, not space, when we put things on a circle. It was the momenta, the k's, which were discrete, not the positions of particles. Positions of particles were periodic. The momenta was discrete.
But momentum was discrete only because we assumed
periodicity. we assume the wave function was periodic. Yeah. Yeah, that it comes back to itself after. Yeah, no, you can question that, and in fact, it is legitimate to question it, but not now.
Just a speculative question. If I, in the simplest quantum field theory, if I take the commutation relation between the annihilation and creation operator and change it to to minus delta KL, is that a simple fermion theory, or that just doesn't?
Yeah. Yeah. If you replace commutators by anti-commutators, so the commutator of A and B is AB minus BA. So, yeah, that's equal to the commutator of A with B. And it's anti-symmetric in that if you interchange A and B, it changes sign. The anti-commutator is by definition, and it's usually written this way, AB, it's AB plus BA. Now I saved this for last because it's harder to swallow that AB doesn't, that AB plus BA equals 0. That's harder to swallow than AB minus BA is equal to 0. Here we have, here we have almost everything is normal. A plus times A minus is the same as A minus, A plus times A plus is the same as A plus times A plus in the opposite direction. It's only a small subset of things which are odd, okay? If we were to replace this by anti-commutators, almost everything would be odd. AB plus BA would equal 0 for almost all of the time. So we'll come to that. But such mathematical manipulations define fermions. And fermions are exactly the particles that have a Pauli exclusion principle. You simply can't put two of them into this. Not only do they not like to be in the same state, they can't be in the same state. There's a complete opposite to the notion of stimulated emission. If you have a fermion in a box and you try to create another one with the same momentum or same everything, you can't. You can only put one of them in a state, and that has to be reflected somehow by the algebra of the creation and annihilation operators. There are creation and annihilation operators for fermions, but they're such that the algebra, instead of telling you that they like to come out in the same state, tells you they cannot come out in the same state. So that's, yeah. And if you can't put a lot of them in the same state, it never behaves classically.
Okay, so somebody saying alpha particle is a boson. I can put a bunch of them in the same state, except that alpha particles are
made of fermions. It's weird. If you take two fermions, you make a boson. You cannot put two fermions in the state, but if you make a boson out of two fermions, you can put two bosons in the same state. But that's not the same as putting the fermions in it. It's kind of weird.
Will we see eventually how to put in like an external field?
Yes.
That would, in this, right now there's no, like an external field acting here. There's
yes.
These are all like free particles, right? So.
External fields can either be described as classical external fields, or they can be described as large numbers of quanta. And that's a kind of boundary condition, that the effects of large numbers of quanta should be essentially the same within small deviations from the effect of a classical field. That's of course how a lot of this was deduced, by saying, well, somehow the electromagnetic field has to describe discrete quanta, but when there's a lot of them, it better reduce to the right thing.
For more, please visit us at stanford.edu.